Today we are going to look at what is known as the initial value problem in dynamics or vibrations. So, we are going to look at the initial value problem for continuous systems. So, what is this initial value problem? So, suppose you have let us say a string, and it is given some initial shape or initial velocity distribution over the string. How will the system evolve? So, we want to determine the evolution of this system. So, given this system described by this equation of motion, this boundary conditions and these two initial conditions, how will the system evolve as time progresses? So, this is the central problem in the initial value problem. Now, to solve this problem, there can be various approaches. Today we are going to look at the modal expansion method. The initial value problem can also be solved by the Laplace transform method. We are going to look at this Laplace transform method slightly later. So, we are going to concentrate today on the mostly modal expansion method. So, now, we have performed modal analysis of this kind of systems, and we have observed that when we have a self adjoint system, which is to say that the stiffness operator is self adjoint, then the eigenvalue problem has real eigen values and real eigen functions. Now, these eigen functions have this additional property that they form a complete basis this is the underlying thing that is used in modal expansion method. So, this property is of fundamental importance in the modal expansion method. So, what is this complete basis? We have discussed that suppose let us consider the string again. So, the solution was obtained was first considered. So, the general solution we have expressed in this form. Which I can write like this. Now, what this says is that, say for example, at a certain time instant t, the solution or this field variable is an infinite expansion in terms of these eigenfunctions. Which for the string it happens to be, so for a fixed string it happens to be this sin k pi x over L. Now, when we say that this is a general solution, that means any shape of the string should be can be represented by this expansion. So, the key word here is any shape. So, any arbitrary shape of the string can be represented by an expansion of this type. So, and we have also discussed that these eigenfunctions are orthogonal. So, if I make want to have a visualization of this, that these eigenfunctions are orthogonal and this forms a function space with this as we call as the basis. Now, of course, there are infinitely many basis functions. Here I am drawing only 3, and with a slight stretch of imagination you can very well imagine that there are infinitely many such axes which are all orthogonal to one another to represent this orthogonality property with respect to a certain inner product that we have discussed. So, in such a space which is known as the configuration space or the modal space, in such a space a point with coordinates p 1, p 2, p 3, p 4 etcetera So, this point represents the configuration of the string at the time instant when the coordinates are p 1, p 2, p 3 etcetera. So, at any time at a particular time instant, this expansion therefore represents the shape of the string at that time instant. So, this point represents a shape, a configuration of the system, and any shape of the string is a point in this space. There is no shape that lies outside this space. So, this is the important thing. So, any shape of the string can be captured by this expansion. This is known as the expansion theorem, the modal expansion theorem. So, the modal expansion theorem says that any shape of the string can be represented in terms of these eigen functions. So, these eigen functions, they form a complete basis, which means any shape can be represented in this basis. So, what I have shown here in 3 dimensions. Now, this is the key to the modal expansion method for solving the initial value problem. So, for the problem that we have here, this and similar problems we will now try to solve using the modal expansion method. So, let us see this general system with certain boundary conditions, let us say this form, and some initial conditions So, we intend to solve this problem using the expansion this. So, if you substitute this expression here, so this is what you will have. Now, k is a linear differential operator, and the kinds of system we are considering, this k has only spatial derivatives and this is linear. So, therefore, I can interchange the summation and the operator. So, finally, I can simplify this and write So, this is what we obtain. Now, recall that this eigenvalue problem for this system was So, this was the statement of the eigenvalue problem for this system. So, therefore, in this summation I can replace this operator acting on the eigenfunction kth eigenfunction with this, and therefore, I can simplify the whole thing and write like this. Now, this is a summation again in terms of these eigenfunctions. So, I can use now the orthogonality property. So, I will multiply both sides by the jth eigenfunction and integrate over the domain of the problem. So, this I will say will take the inner product with let us say u j. If I take inner product with u j, then that filters out the jth term in this expansion. So, I will have and this I can do for all j's, all values of j, and the solution, the general solution of this system can be easily written as and therefore, I will substitute this in the original expansion and write so this is our general solution. Now, once I have this general solution, now I have to use the initial conditions. Let us say these are the initial conditions that are specified for the system. Now, using these initial conditions, we have to actually solve for these coefficients C j and S j. Now, let us see how we can do that. So, substituting this expression in the initial conditions, so this is from the first initial condition, and from the second initial condition this so we have to solve for the coefficients. So, there are infinitely many coefficients. So, for C j and similarly infinite coefficients for S j, and we have these two equations. But then remember that these eigen functions, they are orthogonal. So, we can use once again the inner product. So, suppose I take the inner product with let us say u k, then I can write so once I take inner product with u k, this filters the kth term. And that gives us, so if I write in the integral form, so that solves for all the C k. Similarly, so that solves for all the values of S k. So, once that is done, I have all these expressions, all these values of C k and S k. So, which I can substitute here and I have the final solution. So, we have solved the initial value problem using the modal expansion technique. Now, let us look at some examples of actual systems. So, the first example that we are going to see is shown in this in this slide. So, this is the collapse of a stretched bar. So, what we have is so we have a fixed free bar which is under tension because of this string. So, here there is a string which is attached to this free end of the bar and it is under a tension capital T. So, naturally this bar is under extension. Now, imagine that you cut this string. So, this string snaps. So, when the string snaps, this bar is going to collapse back. So, we are going to study the collapse of this bar. So, let us look at let us mathematically formulate the problem. So, we have this bar, this is a uniform bar. So, we are going to formulate the problem at the moment the string snaps. So, in that case the right end of the bar is force free. So, this boundary condition zero. Now, the initial conditions. So, you can very well you can find out the initial conditions. So, here what was the condition that this was under a tension T. So, you can write the strain in the bar So, that is del u del x, the stress in the bar is the Young's modulus times the strain and when this was under the tension T. So, the force was T, which is sigma times the area of cross section of the bar So, when the bar was under this tension, so this was the condition, this is the equation of statics of the bar, which can be very easily integrated out to determine since at x equal to 0 u is 0. So, the constant of integration is 0. So, this is the initial condition of the bar. And the initial velocity, as soon as the string snaps, the initial velocity is 0. So, this is our problem. This is the initial value problem for this collapsing bar. So, as usual we are going to, as we have just now discussed, we are going to express the solution of this collapsing bar in terms of its eigenfunctions. So, the eigenfunctions of a fixed free bar, they are given by so these are the eigenfunctions of the fixed free bar that we already know. Here omega k, these are given by these values. So, here this is the general solution and these are the coefficients that we must find out from these initial conditions. So, let us see. So, when you substitute this in the first initial condition, and similarly for the velocity condition, these are all 0. So, this immediately tells us for all k, these coefficients S k must vanish. So, we are left with this. So, we take inner product with this kth eigenfunction, and if you perform this integral, so you multiply this and integrate over the length of the bar. So, you can check so these are the coefficients, and finally therefore the complete solution so the complete solution is now this solution I have plotted at certain time instants in these sets of figures. So, you see at time t equal to 0, this is the actual displacement. You see this is the actual displacement of the bar. So, this line is nothing but T x over E a, this is nothing but T x over E a. So, this is a straight line with x. So, here of course, I am plotting it with this non-dimensional free variable x over L. So, initially the actual displacement is like this. So, as time progresses, so at 0.5 L over C, this is the actual displacement profile of the bar. So, here it is still linear, the same as it was here. So, you can imagine that this portion of the bar does not know as yet that this end has been released. So, this information has progressed in 0.5 L over C time to approximately half. So, it is half of the bar knows that this end has been released, this half still does not know. So, there is a propagation of information from the end which was released at time t equal to 0 into the bar. So, at L over C, the bar comes to complete, the whole of the bar is at the equilibrium configuration, which is not shown in these figures. And then at 0.5 L over C, there is a compression taking place in the bars. Here these are all, the bar is under tension. When it comes to the equilibrium configuration at L over C, the bar is in equilibrium, but then it has acquired velocity. So, it still goes and hits against the or compresses against the wall, and then there is a compression generating in the bar, and that compression is complete at 2 L over C. So, there is a, as you can imagine, there is a propagation of information of this compression wave, as it is usually known as compression and tension wave, that progresses in the bar and it reflects back and forth, and that way the bar is vibrating. Now, this propagation of these waves we are going to discuss in this course at a so, we are going to discuss that in detail later in this course. Now, here I have an animation which shows the same thing. So, as you can see, at this instant, so this instant now the propagation the compression wave is propagating. So, this now it is in tension, on this side it is compression, and this wave propagates back and forth in the bar, which is shown in this animation. Next, let us look at the another initial value problem, where we are going to have velocity initial condition. So, let us consider a string on which I specify a velocity profile. So, the velocity profile that I have considered. So, we will consider that the initial displacement of the string is 0, but the velocity has this profile. So, let me mathematically formulate the problem. So, the initial displacement of the string is 0, while the velocity is given So, we have velocity profile like this over this region. So, velocity initial condition is provided only over this small region, which is of length 1/5 the length of the string. So, central portion we have this kind of a profile. So, for this problem, once again so we consider a solution of this form. Now, when you substitute this solution in the initial conditions, you will obtain these two equations. So, you have to solve these two equations in order to obtain the coefficient. So, immediately you can from here it is immediate that all the C k's will be 0, while if you once again take the inner product and solve this problem. So, I mean these conditions, solve for the coefficients S k, then S k turns out to be for k 1 3 5. So, for all odd values of k we have this and 0 for all the even values. So, for all the even values S k is 0, for all the odd values we have this expression of S k. So, so now with these expressions in here you can write down the solution of the string, of the motion of the string. So, here I have the snapshots of the string at certain time instants. So, at time t equal to 0, as you can realize that the string is in equilibrium position. So, I have not shown that at 0.05 t equal to 0.05 there is a hump that is developed in the string, and as time progresses 0.25 L over C, this hump it spreads in the string, but see this portion of the string yet does not know that a disturbance is has been created in the string. At this time instant you see the full string is displaced. Beyond this the disturbance reflects back from these fixed ends and the hump shrinks, and then it comes to the other side of the equilibrium position of the string. So, this shows this animation. So, as you can see that the hump develops, spreads, reflects, collapses and comes on the other side and does the same thing. Remember that this is a slow motion of what actually happens. I mean this progression of waves possibly will not be cannot be observed by the human eye as such. You have to see it in slow motion to observe this kind of propagation of disturbance. So, we have looked at the initial value problem for continuous systems, and we have considered two examples, and using the modal expansion technique we have solved this problem. Now, let us briefly finally look at this initial value problem, how an initial value problem can be actually converted to a forced vibration problem or a force dynamics of a continuous system. Now, this is very interesting because then once we discuss the forced vibration analysis, the methods that we discuss there will be applicable for solving the initial value problem as well. So, which means that we can solve the forced dynamics or the forced or the initial value problem as a forced vibration problem. So, we then have a unified way of treating initial value problem, force dynamics, etc. So, let us look at this conversion of an initial value problem to a forced problem. Now, you see this we have been considering, let us say, this kind of a system and with certain let us say boundary conditions and initial conditions. Now, if you take the Laplace transform of this equation. So, we define this Laplace transform So, if you define the Laplace transform in this manner, then in the Laplace domain. So, here S is the Laplace variable. So, in the Laplace domain you can write this you can very easily check. So, this is what you are going to get. So, this is the equation in the Laplace domain. Now, so this is for this problem with these initial conditions. Now, the same equation can be obtained. So, this same equation in the Laplace domain can be obtained for this system. So, the in the Laplace domain, the equation of motion for this system is same as the Laplace transform of this equation, but now you see this system has 0 initial conditions. So, here instead of these initial conditions, non-zero initial conditions, we have this forcing, this inhomogeneity in the equation of motion. So, we have been able to convert a system with initial conditions to a system with 0 initial conditions, but with forcing. So, this is so this is a system which is now a forced system with 0 initial conditions, and therefore, the solution of this will be the solution of the original system with these non-zero initial conditions. So, this way we can convert or bring an initial condition problem or convert an initial condition problem to a forced vibration or force dynamics problem. So, in this lecture we have looked at the initial value problem. We have solved using the modal and expansion technique. We have looked at some examples of how the solution behaves, and we have found some interesting we have made some interesting observations in this solution, how the motion actually takes place as a propagation of disturbance in the continuous system. And finally, we have looked at converting an initial value problem to a forced vibration problem. And so, with this we can solve the initial value problem and the force dynamics problem in a unified manner in a later lecture. So, with that we conclude this lecture.